In this video, I'm going to talk about trees and graphs, the two important data structures. So, what is a tree? A tree is a data structure composed of nodes. The root node has 0 or more trinodes, and each trinode has 0 or more trinodes, and so on. So in this example, we can see that the root is the node 1. Node 1 has 2 children, node 2 and 3. Node 2 in its turn has node 4 and 5 as the children, and so on. Now we talked about tree types. We classify trees as binary trees and regular trees. A binary tree is a tree of which each node has up to 2 children. If a node has no child, then we call it a leaf. Now we look at several examples. The example for a tree, which is a tree of which each path represents a word. A tree, also called a prefix tree. Each node stores a character, and each path represents a word. Let's look at the example. You can see this path represents the word a or a. Another path represents the word in. And the next represents the word is. The word that stores the pound is to represent the end of the word. Also, we can see other words such as tavern, such as there, and such as town. Also the. Example for a binary tree, which is an expression tree. The expression tree represents an arithmetic expression. For example, 10 plus 6 divided by 2 minus 4 times 3. The root node and the interior nodes contain operations, and the leaf nodes contain operands. As you can see here. So let's look at the implementation of a tree node in Python. Here we have a class, namely node. And then we have a constructor. A constructor basically is a method with a special name in it. And here I have a note saying either init method self refers to the newly created object based on that class, and in other class methods it refers to the instance whose method was called. Now let's look at this method of the constructor. We have arguments such as self and data. By default, data is none. So if you call the method and you don't pass anything, then data is by default none. So in the constructor, data is passed to it and then is stored in the variable data. And also another variable, which is children. The children of the node is initialized with an empty array or an empty list. In Python, we use a list to represent array. Also, we have another method, namely add child, for adding a child. So in the method, we call the append method of the list children to append the object which is passed to the method. Now we look at the implementation of a binary tree node in Python. Recall that a binary tree node has up to 2 children. So we specify that here in the list of arguments. We specify the left node and the right node arguments. If nothing is passed, then left by default is none and right by default is none. So in the constructor, data by default is none if you don't pass anything to the object. So data is then stored to the variable data of the newly created object based on this class. So data is stored in the variable data, and left is stored in the variable left, and right is stored in the variable right. Okay, now we also talked about binary trees vs binary search trees. A binary search tree is a tree in which each node's key is greater than or equal to the keys at the left subtree and smaller than or equal to the keys at the right subtree. So look at the example on the left. Look at the right subtree. We can see that node 10 here is or has the key of 10, which is actually greater than 8. Also, node 8 is actually greater than 4 in terms of keys. So this is not a binary search tree, just a binary tree. On the right side, this is a case of binary search trees, because if you look at the tree, node 1 is less than 3, and 3 is in its turn less than 6. Look at the left node of 6. We have 4. 4 is less than 6. And we look at the right node of 6, which is 7. 7 is greater than 6. Further, look at node 8. Node 8 is greater than 3. So from left to right, we see it follows the property of the binary search tree. Going further to the right, 10 is greater than 8, 14 is greater than 10, and 13, which is on the left of 14, so is less than 14. So this is a case of a binary search tree. Next, we talked about complete vs not complete binary trees. A complete binary tree is a binary tree in which every level is completely filled, and probably except at the last level, with filling order from left to right. So look at the example. The example on the left is the example for a complete binary tree. And we can see that each level is completely filled. Node 1 has the left and the right node, and node 2 has the left and the right node. Node 3 has the left node and doesn't have the one on the right. So this doesn't have, this tree doesn't have the most right node at the bottom level, and so it is a complete binary tree. Look at the example on the right. Now, node 3 misses the left node, and so it is a not complete binary tree, because that missing didn't follow the order of filling from left to right. Missing is here. In the other case, the missing is actually the most last, the most right at the bottom level. Next, we talked about full binary trees vs not full binary trees. In a full binary tree, every node has either 2 children or 0 child. So look at the example on the left. This is the case of a full binary tree. We can see that every node has either 2 children or 0 child. Right? That node has 2 children. Also, on its turn has 2 children. And this leaf doesn't have, or we can say 0 child, has 0 child. And actually, this should have a child in order to be a full binary tree. The example on the right, look at it, we can see that with this case, this node has only 1 child. So it is not a full binary tree. A perfect binary tree is both full and complete binary tree. As you can see in the example graph, example tree, sorry. How can we traverse through a binary tree? There are 3 types of tree traversals: preorder, postorder, and inorder. With preorder traversal, we visit the root and the left subtree and then the right subtree. In postorder traversal, we visit the left subtree, then the right subtree, and then the root finally. And then eventually, finally, with inorder traversal, we visit the left subtree, then the root, and the right subtree. Let's look at an example. Given this binary tree with preorder traversal, we start with the root, which is node 1. So recall that preorder traversal, we visit the root and then the left subtree and then the right subtree. So we visit the root, which is node 1, and then the left subtree, the root of it is node 2. And in its turn, in the subtree on the left, we visit its left subtree, which is node 4. Node 4 doesn't have any child. So once we are done with node 4, we visit node 5. Once we are done with node 5, we are done with the left subtree. We're done with the whole left subtree of node 1. Then we move on to the right subtree of node 1. The root of the right subtree is node 3. In this subtree, in this turn, we visit the left subtree. The left subtree has node 6, which doesn't have any child. So we visit 6. And because node 3 doesn't have any child, so once we are done with 6, we are done with the whole right subtree. Then you can write the order of visiting: 1, 2, 4, 5, 3, and 6, which is actually what we have gone through. Now let's look at Postorder Traversal. With Postorder Traversal, we start with the left subtree, the right subtree, and then the root. So we start checking out node 1, which is the root. In Postorder Traversal, we visit the subtree on the left of node 1. So this is the subtree on the left. We check the root of that subtree, which is node 2, and continue traversing using Postorder Traversal. In this subtree, we have to visit the subtree on the left, which is actually node 4. So node 4 is then the first node that we visit. Once we are done with node 4, we move on to the right subtree of node 2. We move on to node 5. And once you're done with 5, we visit the root of that subtree, which is node 2. So you can see here, the order of visiting or traversing is 4, 5, then 2. So once we are done with the left subtree of node 1, the whole subtree here, we move on to the right subtree of node 1. The root of the right subtree is node 3. So following this type of traversal, we visit the left subtree of node 3 first, which contains only node 6. And there is nothing on the right of 3. So once we are done with 6, because we have nothing on the right, we visit the root which is node 3. And once you're done with 3, as you can see here, right, node, the order of nodes is 6 and 3. So once you're done with the right subtree, we visit the root of the tree, which is node 1. And finally, we have the whole order of visiting. Now finally, we look at Inorder Traversal. So let's recall that in Inorder Traversal, we visit the left subtree, the root, and then the right subtree. So first, let's start checking out the root. Which, regarding the root, which is node 1, we visit the left subtree first. And following the same type, looking at node 2, we have to visit the left subtree of 2 first, which is node 4. 4 doesn't have any children. So once we're done with 4, we're done. So once we're done with 4, we go back and visit the root of that subtree, which is 2. Once we're done with 2, we visit 5. So that we follow the order from left to the root and to the right. So you can see here the order of the first 3 nodes are 4, 2, and 5. Up to this point, we are done with the left subtree of 1. And following the Inorder Traversal, we then visit node 1, which is the root. And then we visit the right subtree of 1. The right subtree of 1 has 2 nodes, 3 and 6. So follow the same pattern. Right? We look at node 3 in the subtree on the right. So with that subtree, we have to visit the subtree of 3, which has only 1 node, node 6. With only 6, we visit the root of the right subtree. And because we have nothing on the right of 3, right? Because if we have something and we would visit it, but because we have nothing, so once we're done with 3, we are done with we're done with the subtree on the right, and then we're done. You can see the order of those nodes 6 and 3. Okay, now we talk about 2 special binary tree, which is min heaps and max heaps. Here we only discuss min heaps, and it is similar for max heaps. A min heap is a complete binary tree in which every level is completely filled except the last level, with the filling order from left to right. Each node is smaller than its children. This is important. And so the root is the minimum. In the case of a max heap, the root is the maximum. So if you have to look for the minimum, in the case of the min heap, you look at the root, and also in the case of max heaps, you look at the root for the maximum. Easy, right? Okay. We consider two key operations. And again, we only discuss min heaps. The first operation is insert. Insert, we insert at the bottom rightmost spot, then fix the heap property by swapping the new node with its parent. And the time complexity is O log n. So let's look at the example. We have a tree, basically the min heap. We insert node 2. We insert at the bottom rightmost spot, and then we fix the heap property. Looking at node 7, node 7 is greater than node 2, and here we talk about the key. We talk about the key, which is 7, and greater than the key of the other node, which is 2. So we have to fix it. We have to swap the two nodes. So then we bubble node 2 up. Then we look at node 4. Node 4 is greater than node 2. We need to fix this. And again, we swap the two nodes, 4 and 2. And finally, we come up with this. And 2 is at the root and is the minimum. Another operation is min extraction. We extract the minimum by deleting the minimum at the top and swap it with the last element in the heap. Then fix the heap by swapping it with its children. The time complexity of this operation is O log n. So in this example, we extract the minimum and we delete the minimum. The last element in the heap is 96. So we swap it with the minimum. And then 96 is at the root. 96 is greater than 23. We need to fix it. So we swap 96 and 23. Node 96 is moved down. Now looking at this, we can see that 96 is greater than 74. And this violates the property of min heaps. We need to fix it. We swap in this case actually 96 also greater than 32, and here we select the smallest element, so we swap 96 and 32, and finally we have this. Up to this point, we have finished all the slides regarding trees. Let's start talking about the graph. A graph is a collection of nodes or vertices with edges in between. An edge is denoted as E, which connects between node U and V. Node U is called the source and node V is called the sink. A tree actually is a type of graph, but without any cycle. This example shows a graph. We will go into several examples later. We categorize graphs as directed and undirected graphs. A directed graph is like a one-way street. To describe a directed graph, we use arrows. For example, with the graph on the left, which is a directed graph, the edge between 1 and 2, we use an arrow. From 1, we can get to 2. But from 2, we cannot get to 1. And this is like a one-way street. In the example on the right, this is the case of undirected graph. And it's more like a two-way street. And between nodes, we only use a line, not an arrow. A graph can have cycles. A cyclic graphs are ones without cycles. Looking at the some examples, the example on the left, is the example for undirected graph, and that is a cycle. And the example on the right is the case for directed graph, in which we can see the cycle. From A, we can get to B. From B, we get to C. And from C, we can get to A. A path, by definition, is a sequence of vertices. If a path exists from node U to node V, then we say node V is reachable from node U. Here we use the words equally node and vertex. Path length is the number of edges in the path it traverses. How can we represent a graph? There may be two ways, using either adjacency list or adjacency matrix. So first, let's talk about using adjacency list. Here, each vertex or node stores a list of adjacent vertices. So, given the graph, this graph, node 1 has a list of adjacent nodes such as 3, 4, and 2. So node 1 stores a list of node 2, 3, and 4. And similarly, node 2 store a list which has only one node, which is node 3. And similarly, node 3 stores a list of adjacent nodes which has only node 2. And finally, node 5 is here. Node 5 can reach node 2, so the adjacent list has only node 2. In another implementation, we can, or each node can store a linked list of adjacent vertices. So instead of using an array or a list in Python, we use a linked list. So node 1 previously stored a list of node 2, 3, and 4. Now it stores a linked list. The linked list has node 2 points to node 3. And node 3 in this turn points to node 4, and that is the last node in the linked list. Similarly, we can see the linked list for node 2, the linked list for node 3, the linked list for node 4, and finally the linked list for node 5. All the linked lists have only one node in them. Another way of graph representation is to use adjacency matrix. So in an n by n Boolean matrix A, in which A I j equal to 1 indicates an edge from node I to node j. And n here is the number of nodes or vertices. In the case of an undirected graph, then we see a symmetric matrix. Now, let's look at the same graph as we see before. Node 1 can reach node 2, 3, and 4. So in row 1, at column 2, 3, and 4, we have 1. Look at node 2. Node 2 can reach node 3. So at column 3, we have 1. Let's look at node 3. Node 3 can reach node 2. So in column 2, we have 1. Now look at node 4. Node 4 has an edge to itself. So we have 1 at column 4. And finally, node 5 can reach node 2. Then we have 1 in column 2. Let's see how graphs are implemented in Python. So similarly, just like the implementation of tree nodes, we have a class, namely node, and in the constructor, we have self and data. Data by default is none. So if you call the instructor, basically when you create an object, and if you don't pass anything to the instructor, then data by default is none, is passed to it. So data is stored in the variable data of the created object self, right? And another variable, namely children, is initialized with an empty array or list. And the other method is for adding children, just like what we have already discussed in trees. We also have another class, namely graph, because a node may not reach every node in the graph, so we need this. And nodes is initialized with an empty array or list. How can we search through a graph? There may be two ways for searching, either using depth first search or DFS, or breadth first search or BFS. With DFS, we start at the root and then explore each branch completely before moving on to the next branch. And with BFS, we start at the root, explore each neighbor before going on any of their children. So let's see how DFS is implemented in Python. Here we have a method, namely DFS, with two arguments or two parameters, graph and start. And in the method, we have two variables, visited and stacked. Visited is initialized with an empty set, and stacked is initialized with a list that has one element, which is start. So start was passed to it and then put in the list. Then we have a loop, a while loop. While stacked is not empty, then do something. So given, let's say, this graph, then if you start with A, then A is put in the stack first. And then in the loop, you pop it out. You pop the element on the top of the stack and store it to vertex. So if that vertex or node is not visited yet, then add it to the set, to the visited set, and then extend the stack. So this is the data. This is the data. The graph has the graph is basically a dictionary. If you say graph A, then you get to the values of that corresponding key, which is a list of containing B and C. So when you call graph and then give it a node, you get to the children or the adjacent nodes of that vertex. And then you remove the ones that have been visited. So the rest is the ones that haven't been visited yet. Then add them to the stack, and then to be they are to be visited later. And in the next iteration, you pop the unvisited nodes from the stack again and again to be visit. This is an iterative method. So the order of visiting would be A, and then B, and then D, and then C, and then E, and then F. Okay. Now let's see how we can modify the previous implementation to recursive, to be recursive. So recursive meaning that you are going to call the method from itself. So the name of the method is DFS with a number of arguments. So visited by default is none. So if you haven't visited any node yet, then visited is initialized with an empty set, and later on passed to other function called recursively. So later in other next course, visited is not none anymore. Okay, let's look at the next slide. If you passed a start node to DFS, then it is added to the set, the visited set. And then you have a loop. You loop for every node that you haven't visited. This is just like what we saw previously in the iterative implementation. Then you call DFS, you call itself recursively, and tell that function call to start with the next node which you haven't visited, and also pass the list of nodes which have been already visited. So this is the recursive implementation of depth first search method. And again, if you look at the order of nodes, dot R visited, then it is A, and then B, and then D, and then C, and then E, and then F. So basically, it is when you start with a node and you visit the whole branch, your whole branch, before moving to the next branch, etc. Now let's look at another method for searching, breadth first search, or BFS, how we implement it in Python. So it's important that in BFS we use a queue. It's important. A queue allows you to, let's say you start with A, and then next you are going to visit B and C, and then D, E, F. So visited is initialized with an empty set, and queue is initialized with an empty list or array with one single element, which is the start node. And why queue is not an empty set? You pop the first element from queue, which is the one at the bottom of the queue. And store to vertex. So if vertex is not being visited, meaning if the node is not visited yet, then add it to the set, to the visited set. And then put all the nodes that haven't been visited to the queue. So in the next iteration, you continue pulling out from the queue. Store to vertex. And so on. So the order of visiting is A, and then B, C, and then D, F. And this slide just summarizes the difference in the searches using BFS and DFS. What is bidirectional search? This is used to find the shortest path between the source and the destination node, usually by two simultaneous BMS searches from each node. The path is found when the searches collide. So as you can see in this example, starting from O for origin to D for destination, using bidirectional search, somehow the searches collide in the middle.